Okay, so we've already talked about volume in that last exam, and that was specifically volume by what we call either disks or, if the disks had a hole in them, shells. Washers. So now we're going to talk about a different method called volume by shells. And so the disk method, the washer method, obviously is great, works great, but there's sometimes it doesn't work so well, and so we have this alternate method. So the disk and the washer method, of course, used disks or washers, and so the idea was to find the cross-sectional area of a disk or a washer and then integrate it. So this will be similar, just a different shape. So let's take a look at this first example and see why we would like to use a different method, and why sometimes the disk or washer method doesn't quite work. So let's say we want to find the volume here on this example by rotating this region, and it's bounded by 2x squared minus x cubed, and the axis about the y-axis. So here's my region, and again, we want to spin this around the y-axis. So if we were to make a slice, right, obviously, which we have here, it would create, of course, a washer, right, because this would be empty in here. And so we'd need this distance. This is the XL, the left, and then we'd need this distance here, and we'd also need to start at 0 and finish at this point here. So you can see already there's a problem, right? So at this point, first of all, in order to figure out that y value, I'd have to find the max of this function. So that's the first problem. The second problem is, if we're going to do it this way in terms of y, I need everything in terms of x equals stuff and y, and do you want to go ahead and solve this for x equals stuff and y? No, in fact you can't. So it's examples like this where we want to employ a different method, and that's this method by shells. So first of all, we need to talk about the shell. What is it, right? It's basically a hollow cylinder. So a lot of people say looks like a toilet paper roll or a paper towel roll. If that helps, great. But it's basically a larger cylinder with a smaller cylinder cut out of it. So it's a hollow cylinder essentially. So you can see I have this this inner radius, this outer radius, and this height. So again, if I were to find the volume of this piece in red here, I just take the large cylinder and subtract the small cylinder, right? So it's pi r2 squared h, that's the volume of the big cylinder. I subtract this, which is the volume of the small cylinder, and the resulting volume is what I'm looking for. So these are what you're going to need to focus on, not disks or washers, but these things called shells. Okay, and so if we take a look at this, you can see we have the pi and the h, excuse me, common to both, and so our volume that we're looking at is actually going to end up being 2 pi r h times delta r, where delta r is that change in radius, or what we're calling that thickness. Okay. Another way to think about it is, instead of finding the area of a disk, what are you trying to find? You're trying to find the circumference and the height of the shells. Okay. The circumference and the height of the shells. The thickness will be the dr dx. That'll take care of itself. So how do we figure out the volume? The volume is equal to the integral from a to b of 2 pi x f of x dx. Again, this is the circumference, this is the height, and this, you don't have to worry about, that's the thickness. Okay? So, let's go back to that original example. This is what we're talking about. So you want to, of course, sketch in a sample shell. So notice I have height, and I'm basically taking a rectangle and rotating it around the y-axis. That's what I'm doing to create the shell. You could put the other side here if you want. It's not necessary. What do you need to find? On the left or the right-hand side, you should always write radius, circumference, and height. That's what you need. Okay? So the radius is obviously x, as x varies from 0 all the way up to 2. Okay? So that's why my radius, or r, is x. The circumference is obviously 2 pi times the radius. And what's the height? Well, this is the height here. It's the function. So that's where that comes from. Once I have that information, the setup again is circumference times height dx. And again, we're going from these shells start at 0 and they go all the way to 2. Right? If I were to sketch a smaller shell in here, it would look like this. Doesn't matter what your shell, where you place your shell. It's always going to have the same radius, circumference, and height. The rest of this should be no problem by now. Okay, some integration, fill it out. Let's take a look at this example. Find the volume by rotating the region bounded by root x and y equal x squared about the y-axis. And I'm telling you to use shells. Other than the homework and the worksheet on an exam, if I don't think I'll say it, I guess I'll let you know when I make up the exam. But if I don't say it, you can use whatever method works for you. So here's the region that we're talking about. Right, we have the root x and the x squared. Here's the root x. Here's, of course, the x squared. They cross over at 1 and at 0. So I have a sample rectangle. I'm going to rotate that rectangle around. Again, you want to put in the rest of the shell. You can, you don't have to. What are we looking for? Radius, circumference, and height. Again, the radius is x. The circumference is, of course, 2 pi times that. And now the height, which is this distance here, is the top function minus the bottom function. So it's root x minus x squared. Once you have that information, simply the circumference times height dx. Again, simplify, a couple of power rules, not a big deal after that. Let's find the volume by rotating the region bounded by root x about the x-axis from 0 to 1. Right? We're going to use shells. So here's the region that we have. Here's my sample rectangle, and that's again rotated this way. Again, if you want to put the rest of that shell, you can. It's not necessary. So again, we need radius, circumference, and height. Now notice that because the shell is on its side, we have to do everything in terms of y. So again, the radius, which is this, is y, as y varies from 0 to 1. The circumference is, of course, 2 pi times that. And again, we have to be careful because we need this height here. So that's this larger piece here is what? Well, that's 1, because all of these shells are over here at 1. And this smaller piece here is the function. Again, because everything's in terms of y, even though it's y, excuse me, even though it's y equal root x, I need it as x equals stuff in y. So if y is root x, x is y squared. So this is actually y squared. So this height that we're looking for is 1 minus y squared. That's where that comes from. Again, setting up the integral, we have the following here, and then it's a simple integration, and you get the answer. Now, notice that if we take this exact same example and use our disks, right, what would that look like? Well, again, it's the same picture, of course. This is what's getting rotated, and so if we take a look at a disk, what do we need there? We need the area of the disk, right? So the area is pi r squared, so r is simply root x. So it's pi root x squared, which is pi x, and so the integration is much simpler, right? Moral of the story being, shells isn't always the best way to go about this. Sometimes shells work great because you can't even do disks. Sometimes not so much, as in this example. Okay, so unless I specify, use whatever works, whatever's easier for you. Okay. So here you go. Right, I said. We just covered it in the section, so I'm going to ask you to use the shells for these two things on the worksheet. Notice that one is about the y, the other is about the x. So one will be all in terms of x, one will be in terms of y. And then similar kind of stuff in homework. Okay.